Okay, good afternoon, everyone. Welcome. Today we have special guy. We have Rhett, our Rhett, like you like in the email. So I assume that all of you know Rhett. Half of the people here worked with him in Santa R&D, but the other one, Rhett did his electrical engineering here at UNSW. He finished in '97 and then joined Pacific Solar that become CSG, that become Santa R&D Australia. And the last thing that he did in Santa R&D Australia was the technical director. He joined us in mid-2013 and started his PhD. He's focused on statistical model for PV, and that's a great topic and very interesting for most of us. He also established his company, and he worked half-half, or roughly. Anyway, I push him, so he finished almost all his PhD in this presentation. So please welcome Rhett.
Thanks, Ziv. Yeah, I knew agreeing to a seminar would force me to get through some of this work, but it was there was, as is often the case, some of these problems are harder to solve than you think. But that's good because that's what makes them a PhD. Otherwise, you know, it'd be hard to convince the examiners. So I'm going to talk a lot today about variance because it's something that a lot of us often don't think about. So roughly sort of the first half of the presentation, I'm going to talk a little bit about variance and the context for the research and why I'm doing it. And this is quite interesting because I think there's lots of research questions in this area. And, you know, if any of you are looking for more research questions, maybe you'll be able to spot a few. And in the second half, I look more at some of my results. So I've got quite a few slides, so I can, you know, rush or I can slow down over bits. There's, you know, often, in many cases, I'll just be throwing up, you know, figures where there's a lot of information and a lot of thinking that sits behind them. So, you know, by all means, if anyone's feeling uncomfortable with anything I say, you can yell out and we can talk about it some more, or you can come up and talk about it to me afterwards if that's more your style. So I'll keep going. So that's what I'm looking at today. So, you know, I'm going to look at the context, why we care about variance, the path models and the solutions to them are one of the approaches that I'm taking in my PhD to solve some of these variance questions. And then what do we actually do with this knowledge when we have it? I mean, sometimes it's powerful and sometimes it's annoying, you know, like once you know more things and you've got to sort of be obliged to do something about them, okay? So this is a slide that I often start off with, and anyone who's been to see other seminars I've done will have seen it before. I like this slide because for me it puts into context how important manufacturing is in actually lowering the cost of PV, which is the thing that many of us are motivated to do by our involvement with this area and this field. So it's quite hard to find sort of a breakdown of where all the different sort of improvements in cost and stuff have come over the years, but this is one, you know, it's quite old now. It's, you know, it's only a few years ago that it was published, but the data is reasonably old. And it comes up with this idea that, you know, something like 40% is related to manufacturing. I would sort of contend that that there's lots of ways to look at this. That if we actually look at costs and if we assume a decoupling between costs and efficiency, you could say that efficiency improvements are responsible for as little as 2% of the overall improvement. Now, that's clearly an exaggeration in the other direction, which is probably as wrong as the sort of 30-40% number. But somewhere in between we're going to get the right answer. The point is that looking into manufacturing and doing research around manufacturing is really quite important. It's at least as important as looking into efficiency. And we all know that we have a good technology on our hands here. So it's worth looking around, you know, why we don't have a lot of discussion in manufacturing, particularly around the data analysis topics that I'm looking at. Now, photovoltaic manufacturing is, you know, it's reasonably accurately described as as an industry in its adolescence, you know, we have a turbulent market, we have sort of turbulent technology development, things are sort of changing all the time. This sort of approach to market is quite rudimentary, and you know, we can say it's sort of based on a technology push, which is this notion of this is what we make, you guys should buy it, as opposed to, you know, a market pull type of situation of more mature products, particularly consumer products. Now, one of the things that really interests me is that, unlike in other manufacturing sectors, there's nearly nothing in the published literature around the development and optimization from a data perspective. And it's interesting to think about why, because there's some great review papers out there which look at, you know, hundreds really of papers on this sort of topic from other industries, you know, chemical industry, food industry, you know, paper industry, all of these sorts of industries, which are reasonably comparable. Now, there's a lot of reasons to think about why. It's interesting to think about these because mostly this gives some understanding of how we can improve this area. My favourite, you know, data sensitivity, all this sort of stuff, everyone sort of knows this sort of stuff. You know, this whole thing here, this one, the little work being done, you know, I don't know whether that's actually true. I've only worked in a few companies and I can only comment on that. I haven't worked for every company. I don't know what goes on in every company. The last one is another really important thing which we'll come back to as well, and that we have a reasonably unique situation in photovoltaic manufacturing in that we can directly measure the power of the cell, and sort of we're a little bit spoiled by that, would be my contention, because it's reasonably unusual in other manufacturing to be able to measure something which so directly relates to what you think you want in the quality of your final product. And you know, like what's the single measure of the quality of a car or a foodstuff or something like that? You know, these industries need to go to quite a lot more trouble to develop a notion of what makes a quality product coming out of their manufacturing system. And it's my contention that we need to do exactly the same thing, and to some extent relying upon efficiency, we've been a little bit blinded by those opportunities. So, you know, this is my pretty slide about what I'm doing in my PhD. So my aim is to build sort of multivariate statistical models that start to describe the manufacturing system, as we see happen in other manufacturing sectors. We can improve our understanding of variance and its sources, and therefore we can also optimize how we collect data in the manufacturing system. We can improve our product quality and also start to think around what we actually want out of our manufacturing system. So I call this sort of system level thinking. What do we actually want to see out of it? And how, well, let's look at a couple of things that I've done to try to address this situation. Now, finally, on this sort of introduction context stuff, it's worth thinking about a couple of barriers to why these statistical things aren't studied more in a more widespread way. Now, clearly we have this embedded hatred of statistics, which is really, really good. You know, when I often think about when I'm coming up with new statistical algorithms, whether I need to do things like patent them or trade protect them or whatever, and you don't need to do any of that because people hate statistics and they're not going to try and copy you. So it's great protection of intellectual property inherently. There's this whole thing about getting over this thing of data being sensitive. You know, everyone tells you they're data sensitive. If you get to the right people in any company, they'll admit to you that their data is really not that sensitive. But it tends to be an opinion companies put forward. You know, in all other areas, we just normalise the data. That's really straightforward, okay? And we need to start thinking about the relational values in the solar cells and understanding those a little bit better rather than just the absolute values. And it's also this idea that I think a lot of industries go through, where we're sort of moving from a concept of our industry working in an expert model or our manufacturing working in an expert model more towards an analytics model. So what I mean by that is we're using our analytics to help give us insights rather than just our domain expertise. Okay, and again, that's a trend that you see in other manufacturing areas. So why care about variance at all? Okay, this is the very big question. Now, a really important thing when you're doing manufacturing is this idea of quality, okay? And it's quality in the manufacturing sense of trying to do the same thing every time. So it's a point about consistency. That's really what manufacturing quality is all about. We want to do the same thing every time. We want to make the same thing, okay? Now, mostly when we're looking at our solar production facilities, most people are concerned about the average efficiency of their lines. And probably that's the right thing to do. That's, that seems to be what is the main monetizer in the industry. But this isn't really going to last forever. We're not, manufacturers aren't going to keep getting this steady sort of half to, it's this sort of 0.1 to 0.2% increase a year. That's not going to keep going on forever. It can't, okay? So what comes next? A stable industry is more concerned about the quality. Now, are we there yet? Are we there yet? We're probably not at the point where it's of dominant importance, okay, which is good. Just give me a year or so to figure all this stuff out. And then when it's all worked out, it'll be the biggest issues facing us, maybe. But returning to this notion as well of trying to seek what I would call a genuine quality function for PV manufacturing. Okay, so to move away from this notion that everything we need to know is contained in the efficiency and its derivatives, but actually you try to generate some sort of quality function, which is more what other manufacturing sectors would look at. And sorry, I'll just make my phone go silent. Fortunately, anyone who would ever call me, I think, is in this room. So, okay. Now, one of the reasons that it's hard to improve or hard to get a lot of traction on this variance issue is there's often a lot of stakeholders and it's quite diffuse, who benefits from this. And we also have the supply chains can be quite fragmented in our industry. And this is quite an interesting point to look at because it shows you how where you have to act and the levels you have to act on to get people interested in changing these sorts of things. So, it's interesting to think about that if you're an end-use customer and you were going to go and buy, some modules for your roofs or some, that came from some solar cell production facility, what would you like the performance of that facility to look like? Would you be more concerned about the absolute efficiency of that product, or would you be more concerned about the quality of that product or how tight the distribution is? Now, I'm not going to sort of answer this. I'm more going to pose this rhetorically. If you consider yourself in different sorts of roles, what would you want if you were a cell customer? And what would you want if you actually were the person who sold the cells or the person who were manufacturing the cells? All of these people are actually going to feel a little bit differently about this question, which is why, everyone seems to be able to agree on let's get the efficiency higher, but it's why the variance is sometimes an issue that you can struggle with traction. And the other thing that I'm more interested in as well is what data would you actually want to collect if you cared about this? Now, you very quickly race to the notion here of what is the value proposition for trying to control variance, okay? Because at the end of the day, if you want to convince people that it's important, there has to be money in it. And certainly, like if you wanted to build a business out of advising people around this or helping people with this, which is some of the things that I do in my work, then you want to be able to communicate something about a value proposition. Now, I think this is a really interesting topic, value propositions. It's a really, really fun topic because, in solar cells we have this little thing like we have this cell, okay? And we make, in production lines we just make millions and millions and millions of them a year. And so it's really cool, like if you can find some way to even abstractly justify some small way to improve that thing and then multiply it by a few billion, then you're going to get a really attractive looking number. So it's always really easy to come up with value propositions. But it's really important, I think, to try to come up with ones that are actually based on as much data as you can find and on real operational practice. My favourite one of these in recent years, I read a story a couple of years ago about someone trying to justify the cost of having panel level monitoring. And they justified that cost by saying every panel that drops some power would cost you about $500 in labour to find that panel and replace it. Therefore, we can justify doing this panel level electronics. But the reality is you wouldn't actually do that. You know, if you lost a little bit of power, you wouldn't bother going to try to find the module. You'd go to find it at some point. But you know what I mean? There's, you know, when you actually want to look at your value proposition, you have to look at what you would actually do. Yeah. And so, having said all that, I'm going to make up my own numbers now, which is fun. So we can start to look at some ways that we can start to improve margin with lower variance. So these are ones that I've come across from my own work and my own experience, and there tends to be big ranges on them, but they're quite interesting to look at. And the obvious one that we often look at is electrical yield. This is a really interesting one because I think this comes to fragmentation in our industry, but there's a lot of dishonesty around this number. You know, a lot of people will often run a cell production thing and they'll say my electrical yield cutoff is this and my electrical yield is 99.8% and electrical yield's not a problem, so I'm not going to get any better by improving variance. But then if you actually look what happens right through that factory, you find that what's happening is the bins, the cell packets that they made from the lower two, so that the lower two cell packets from the lower end of production are largely sitting in their inventory. No one really wants them. You know, so the cell guy is feeling good. You know, his electrical yield is 0.2%. But the inventory guy's upset because there's these sort of 5% of cells or whatever that are accumulating in their inventory. Or they somehow convinced the module guy to make the modules and they made low modules, and so the modules are sitting in the inventory, and then one day someone gets annoyed and they just dump the whole lot for 20 cents a watt or something like that. So, I mean, you know, you need to be honest about where electrical yield is actually costing you money. And because there's a lot of fragmentation in the interfaces between the different business units in companies, it's often really hard to get this sort of information. But electrical yield, certainly we tighten the distribution, we can stop those packets and those modules hanging around in inventory. This is an interesting one. It's often not a big cost, but it is often really interesting to experimentalists or people working in labs as well. And that basically, if you can reduce your variance, then you reduce your experimental costs proportionately. Okay, because you need less experiments, or you need smaller experiments to work out your improvements to your line. Yeah. So and most lines have some proportion of production that are allotted to these sorts of experiments, or they have a dedicated line that are allotted to these experiments. But mostly all this sort of stuff is oversubscribed. If you do better variance, you can do much better experiments. That's pretty straightforward. You can save quite a bit of money on that because companies spend a lot of money on their R&D in a manufacturing context. There's this whole sales and logistics idea as well around, this is sort of related to those whole cell packets that are sitting around in production. Then it starts to get really, really interesting. It starts to get less related to my field of expertise, and I have to start relying upon hearsay, which is conversations with friends or scrapings of data I can find in publications. But there's these two things. There's this field installation logistics. So basically, you know, you go and ask someone, what's the difference to the cost of your project if the company delivered one box of modules onto your site? You know, so you've got a however many megawatt development, and the modules came from the manufacturers, and they said, here you go, here's one module, it's the same, put them anywhere. Okay, as opposed to what happens now, which is you get 9 or 12, you know, you get 3 different current classes and 3 or 4 different power classes, and you have to wire them into the right strings and parallel combinations, and it's, you know, again, these are things people are just used to doing, so they just do them, and they sort of think, well, that doesn't really cost us anything, we just do it. But I find that really difficult to believe. And then there's all of these there's other really interesting areas too about what starts to happen in the energy that you make over the life of your system. And this is something that I'm starting to study a little bit more now, because we can make estimates of things like mismatch loss, and we can start to make estimates of things like how modules degrade over their life, and we can tighten all of that stuff up if we have a better quality process. Okay, we have a lower quality process, then that stuff happens over wider bounds and you start to lose more energy. I've just come across a really good data source for starting to track some of this stuff in situ in field developments, and so I'm doing a bit of work on that at the moment. It's a really interesting area and potentially, you know, maybe one of the bigger areas, but you can see what I mean, you know, like the manufacturer has to improve the variance. This guy can see some, you know, this is a system operator and system developer. You know, these guys might be 3, 4, 5 years removed from this guy, you know. So how do we get these sort of ideas to percolate across the supply chain? It's quite an interesting sort of area. Now, there's some substance to these numbers and a little guesswork. You know, I try to have as much substance as I can, but, you know, there's certainly, it's a good initial approximation. There's certainly like a lot of opportunities for, you know, this is to spot the research projects that I was talking about before. There's a lot of opportunities for further work in this area. Okay, so I've talked about why I'm doing all this, okay? I've taken, nearly half of your time to do that, okay? So now I'm going to have a little bit more of a look at some of the statistical methods that I've been looking at to try to do this work. So depending on how you feel about statistics, you know, you might find this better or more interesting or less interesting than the first half. You know, I'm fascinated by this idea of how you can present statistics interestingly. I went to watch a gentleman talk. I can't remember his name now. He one of these professorial lectures, and he was a statistician, tremendously entertaining guy, well renowned as being a great talker. And I thought, oh, that'd be really good. I'll go along and I'll learn about how you can present statistics more interestingly. You know, I think that'll be really good for me. And I went along, and pretty much what I learned is how you present statistics more interestingly is you stop every 3 minutes and crack a joke. But the statistics still remained being largely boring. So, you know, you can pick up some tricks, but some things remain the same. I'll try my best to keep it interesting, but by all means, if you're welcome to ask questions in this bit as well. We'll see how we go. Now, lots of things will move across the screen here to stop you from staying, you know, falling asleep, keep you awake. Okay, so a path model is one of the ways that I'm looking at the moment to model the relationships that I'm seeing in the data. You know, largely what I've done through the course of my PhD is just read a bunch of statistics textbooks to find the right model, basically, to express the data. What this sort of big data science stuff is usually all about is, you know, there's always some sort of relational aspect to your data. There's some way that data clusters together or groups together or relates together, you know, and it's all about finding the right technique that expresses those relationships in some useful way. Path models is a way that I've come across as a way to do that. But, you know, and this is pretty much where I got up to when I told Ziv that I'd do the presentations. I thought I'd finally found my model. We're nearly there. I can do a seminar in a few weeks. But, you know, the path model stuff is quite straightforward. So solving it ended up being much trickier than I thought. That's section 4 though. So if I can explain quickly what a path model is, it's really straightforward. It's essentially just a diagram where you're trying to express the relationships that you get in the data, okay? And it's relationships that you might see in some number of contexts. So typically we would know in most manufacturing data that there's often what is a primary relationship between the short circuit current and the open circuit voltage in the cells that you produce. This is largely derived from the lifetime of the wafer that you've got. So, you know, we'd express this in a path model as we see over here. You know, this sort of diagrammatic nomenclature, you know, as a simple scatter plot as we've seen, and the other thing that we see as a way to relate this data is just simply a correlation matrix, okay? Fairly straightforward. Okay, and then we can start to bring other stuff into this as well. You know, so we start to look at the fill factor, Okay, so we know that there's a relationship between the voltage and the fill factor. That's fairly well known as well. Okay, and there's some correlation matrix that relates this. Okay, and then finally we can start to, we know that there's this relationship, this lifetime relationship between the current and the voltage. We know that there's this diode relationship between the fill factor and the voltage. Okay, what about the fill factor and the current? So we can look at that as a third thing now, and we can look at the correlation matrix associated with that. Now, keep in mind this path diagram here over on the left of the screen. How that's drawn at the moment is that we've got the voltage, and then that's having some influence on the current, and it's through this lifetime relationship, and it's also separately having some influence on the fill factor through this diode relationship. Okay. Now, if this was the only root cause of this underlying relationships in this data, then basically the correlations between the voltage and the current and the voltage and the fill factor respectively would multiply out to give you the correlation between the current and the fill factor. Okay, but it doesn't. Okay, and that's should be no surprise to anyone, because as most people would know, there's other things that cause the current and the voltage to relate to each other. So that's essentially what we're trying to do with these path models. We're trying to look at how these correlations work and how they multiply out to understand and solve for the relationships between these variables. Okay, so what this means in a path model context is that we need another arrow on our diagram, another arrow that just puts a relationship between the current and the fill factor in this case. Okay, so we have now our path model, and we have our correlation matrix that describes it. Okay, now we can start to get a little bit trickier with this path model, and we can start to try to make some implications, okay, about what might be the root cause of these relationships. Okay, and this is where things start to get a little bit interesting. We use what's called in this case a latent variable. Okay, so a latent variable is a variable that we don't directly measure, but it's a variable that we would like to know about or infer. You know, a lot of this path models was first developed in behavioural science, where they would want to know things about people's intelligence in particular areas. You know, and while you can't measure intelligence directly, you can measure, say, scores on a range of tests. And from the relationship in the scores on the range of tests, you might be able to infer something about intelligence as a latent variable. So that was sort of where these were, the original concept of these types of models. But it's used fairly widely in a lot of different fields of science. Okay, so you know, if we take away these paths in the path model, and we say hypothesize a couple of things that might cause these relationships. Okay, so in this case we have something like wafer quality or lifetime, or you know, I'm deliberately vague around how I define these things, because there's lots of ways that you could sort of define these things. A strict definition isn't so important in all cases. What is important is to track the relationship, okay, and to see how that changes in your data over time. And the other thing, like, so a really common thing in a conventional production line that would say govern an interaction between the current and the fill factor is the front screen print grid. Okay, that's a really common one that you see. Okay, so a simple latent variable model like this, it actually has a fairly simple solution. You label all of these paths, you get your correlation matrix, and you can write all of these equations, and you start to be able to solve for these paths and for these sources of variance in your data. Now most of you will know that we've got 3 equations here, and there's 5 things that are unknown, so that's going to be problematic. Okay, there's a couple of different ways around that. We'll talk more about that as the presentation goes on, but for the moment I'm just looking at these, simply what we're trying to do in terms of trying to essentially break apart this correlation matrix into the root causes that are driving the relationships in this data. Okay, so are you convinced by this stuff? You know, like, do you actually think that we can just, invent these latent variables and drop them on a diagram and believe that if we solve for this, we'll actually learn something about the data? Well, the common thing people would think is like, how do we actually even know? How do we know what they are? I've made some things up, but how do we know if they're true? Sorry, are you distracted by that jiggling? I'll hurry through. I didn't think I'd spend this long. I'm a bit distracted by it now. In the end, these are all really interesting questions. The limit to which you know, okay, is entirely determined by how well your path model captures all of the variance to start with, okay? And in a way, what we need to do with this is we need to build a more complete model as a first step, okay? And then we need to, in a way, a good company, when they're running a cell production line, will have a really good sense at any given stage, for instance, of a loss analysis of their cell. So they'll know that their peak or their average cell efficiency is a given number, and they'll have a really good sense of where the losses are in their devices and where they can target those losses, okay? And they don't do this every day in their production, but they keep, they do a few detailed studies and they keep a fairly good sense of what this is. Now, you can do exactly the same thing with variance, okay? So you can know something about where you expect your sources of variance to come from, okay, by doing some sort of detailed study. And then you can use something like these models to help you track these things, okay? But you have to understand where these relationships are to start with. You have to understand, because you're going to, let me sort of jump to this and explain this a little bit more here. So when we start building this more complete path model, we might sort of step back and think, okay, we're going to look at a few more variables now, and we're going to look at a number of things that can cause these interactions between all these variables. So here's a bunch of really common ones that would actually encapsulate a huge amount of the variance in most manufacturing. Okay, so we see here that things start to get awfully complicated, and we also see I'm giving these sort of rounded boxes here rather than circles, because many of these variables we can measure and many of them we can infer as latent variables depending on what situation we might have in the production line. But we can start to go to things like this, and we can look at, well, we've got one variable here and one variable over here that seem to be doing exactly the same thing. Okay, so these models actually get quite complex to solve, and how we can pull these things apart. So it's really important when, to start off with these models to try to make them as complete as possible. And then what we start to do is we start to look at how we can try to work on solving these things and understanding the variance as well as possible. Okay, so if we take things like, say, the grid finger width and the emitter resistivity as an example, we might, how can we actually separate these two effects in a model when they're acting fairly similarly, okay? Now, part of the stuff we can do is we can start to, make simplifications to the model by what we know about where the sources of variance are. We can start to pull some things out, okay? So there's a lot of things that we know that have little influence on this model. Now, silicon thickness, wafer reflectance are good things to pull out of the model. I know from experience of this particular data set that I'm looking at that these things have very little influence on the variance. The silicon nitride might surprise people. It did actually surprise me when I realised, but we can talk about that more later. But taking that at face value for the moment, already there's other things that I haven't included in this data which I know has small impacts, things like wafer area and wafer thickness. So we're always making simplifications in this data. This other thing is really, really useful as well, and this sort of can drive the whole model towards what sort of data we want to collect. So if we're comparing in this instance, say, between the grid finger width and the emitter resistivity, the grid finger width is something that we can measure at the end, whereas the to measure the emitter resistivity, we have to measure it somewhere, usually near the beginning, and we have to track that wafer through. So that can be a more complex piece of information to collect. The grid finger width, while it requires some sophisticated equipment to collect, there's some other analogues which are really, really high quality, such as the bus bar to bus bar resistance, which is usually a nearly zero cost add-on to IV testing, so which will give you largely the same information. So it's about sort of looking at what information you need to collect to try to disentangle as much about the sources of variance as you possibly can. Okay, and even though, so some of the data sets that I worked with are sort of like fully joined data sets. You know, I have data for hundreds of thousands of wafers and all the information right through the production line. To some extent, I'm more interested in these models that just use the end-of-line data, because that's more the general case. That's where most of the manufacturing works. Okay. The other really interesting one to think about is the lifetime parameters. You know, I put a couple of lifetime parameters in here. They're really interesting ones, because they're often ones which are really interesting to us. And theoretically, you know, nearly all of the VOC variation will come from changes in the lifetime, and we can tend to make assumptions about that when we solve these models. But as a latent variable, you can sort of allow that sort of stuff to happen. But if you've actually got a measured variable where that measured variable is trying to accurately represent the lifetime, it's never going to be able to do that perfectly, you know, because you need the right algorithm or the right transformation or the right sort of statistical approach on the particular lifetime data you're collecting, whether it's sort of from a Sinton tester style lifetime or whether it's a PL style measurement. You know, these are all indicators of the lifetime. Okay, so you can start to get a sense for what the difference might be between a latent variable and a measured variable. You know, one is sort of a theoretical construct that in some regards can nearly perfectly meet its aim, and the other one is a measured construct, and you can use them both for different means and against each other to assess the value. Okay. Now, how are we all going? Lots of statistics. Okay, gets a little bit more interesting now. Well, firstly, I've just got one more before it gets interesting. Okay, sorry, you'll have to persist with me here. So yeah, as I talked about, the aim, what I had back here, one iteration of the path model. Okay, so what I'm going to propose now is another one which I think we might actually be able to solve. Okay, so the other one had paths going everywhere and hardly any measured data, and you know, this one is one that we can start to have a go at solving. Okay, so these are all common parameters that we might measure at the end of line. Okay, and as I say, finger width, there's other analogies to that. Okay, and we can start to think about now three latent variables which sit underneath these and cause changes in these variables. So we've got the wafer resistivity, the emitter resistivity, and the final lifetime. Okay, now you know, as a whole, you can sort of, those of you who are really familiar with this sort of stuff could see lots of variance on these sorts of relationships. You know, potentially, you know, we could have some sort of enhanced recombination thing here as a latent variable, but often a well designed model with a J02 component will often be a really, really good representation of that. It sort of really depends on your data set and on your situation and how that is important to you, but there's lots of variance of how you can set these things up, yeah? And to some extent you can be led by the data. Okay, so the problem with you trying to solve these sorts of models, so I thought once I got to here I was nearly done. Okay, I thought what I would do is, yeah, there's a little bit of overlap in the path models, but you know, if I used a few physical models, I'd be able to solve this path model. By physical models, I mean stuff we know about the cell. You know, it's easy to get, say, for instance, derive other relationships between these paths by what you know from the cell, like a physical model of the cell. That combined with the path model, and you can usually have a good fist at solving these things. But it turned out that it wasn't that easy. sadly. Well, sadly because it meant it was more work to get some of this stuff together, but it's good, I guess, because it means there's actually a justifiable PhD in it, you could say, I hope. So part of the problem is that trying to go back to this idea of just using correlations to solve the path diagram can be really problematic. And it's mostly because we have autocorrelation and process drifts and stuff like that. So autocorrelation is just basically a situation where you have the mean of the process drifting over time, which is really common for inline processes, okay? It's not necessarily an indictment at all of PV manufacturing. So, a really good example is here. We can see these sort of two data sets here, and one of them looks like there's a little double distribution. And so as a result, when you're trying to find the relationship between these current and voltage, you get two quite different things, whereas really I think what you want is there's two relationships here, and you want to be able to separate this sort of stuff. So the correlation, this is a really sort of easy example, but there are heaps of examples of this sort of stuff in the data, and it just, I couldn't get consistent solutions to these equations. So I found that in many situations we needed to find some alternative way of expressing the relationship between these variables. And so this is then, this looks really good because it looks like it was all planned, but this comes back to something that I presented back in 2014 where I was looking at the difference, what I call like a vector representation of the change in your data. So I found that if you take a cell at any point in time and look at what changes to make the next cell, that you can express that change as a vector, and you can start to look at the direction of that vector as a key expression of the relational nature of the data. Okay, and so if we go back to that data set that I just showed before, you get these histograms of the angle this time, and they largely overlay, okay, at the modal response. So what that's telling me is that the most common change that's happening in that data set is the same in both of those data sets. But you have other secondary relationships which is causing that spread, okay? Now, so the last 4 weeks of my life have become how you interrogate these relationships a little bit better, okay? And there's a whole heap of really interesting stuff in there, but sadly, I've only got, does anyone have any questions at the end? 3 or 4 minutes to show you. I get all the way to the punchline and now I'm going to rush through it. It becomes quite tricky. You can start to use these things now to interrogate some of the relationships in your underlying data, okay? And we get onto the solutions here. Now, you can start to work through the data pairwise, and I use, so this might sound like a commercial endorsement, but I use software called Jump, which is a really nice way in this data to highlight key sections of the data, and it highlights the data across all of your other graphs. So you can start to do things like here, where you can highlight in, say, the current voltage response, that modal response, and you can start to see that at that modal response, what's the relationship in the other data, okay? And so you can start to pull these things out. You can start to pull out, at your lifetime relationship between current and voltage, what is the actual slope of that relationship? And then what is the slope in your other variables that are happening at the same time? Okay? Now, you can go through this and you can do this for basically like all of the different pairwise relationships that you've got. Okay? Now, what are we really doing here? It's the finger width, sorry, I should rush through this one. The finger width, by the way, is a really bad set of data to do this. In some regards, this shows the limitation of measured data. The measured data on finger width tends to be very noisy, and what tends to happen with that process is it drifts slowly over time as the screen ages, for instance. So it's nearly impossible to pull this sort of data out, that sort of relationship out with a difference relationship. So you have to go back to a good old-fashioned linear regression, but even then you start to see the problems of when you break this up over time here, this data is sort of average data, and it sort of shows you over different periods of time there's different sorts of relationships between these two variables, and that's because of other external influences. So it shows you, you have to sort of, there's ways you can control for this sort of stuff, but it shows you some of the difficulties in solving these models and pulling these relationships out. Okay, we can start to do the same sorts of things with the emitter resistivity. We know the sorts of trends we're looking for. We're looking for where voltage goes up and current goes up and resistance goes up together. We can start to do things like we can start to pick different parts of the vectorial space, and we can start to see things where we have distributions which are significantly different from random, and all these sorts of things. Like it's cool. You can do some cool stuff, but sadly, it's stuff that's really hard to present and hard to probably give due appreciation for some of the trouble you have to go to. But you can see what I mean here. You can start to pick out. It might seem like I've picked this value out of thin air, but you can work your way across this when you know what sort of relationships you're looking for. And basically, when you're you need to have selected these angles for the voltage and the resistance relationship to be able to see relationships in the current and the resistance which start to significantly differ from the background noise signal. So there's a lot involved with pulling all this sort of stuff out. We can do the same sorts of things for the wafer resistivity because we're looking for a slightly different type of interaction here. We're looking for where the current goes up and the voltage goes down and the resistance goes down, and you can start to see where this happens together and pull some of this information out as well. Okay. Now, sorry I had to rush all through that, but to try and get to some of the other final conclusions of the stuff. Now, once these relationships are all known, they can be directly used to calculate the components of the variance in your manufacturing system. Now, most of that involves rotation and projection of the data, which is quite a powerful technique because you can do things like you can progressively and sequentially rotate major sources of variance out of the data, and then you can actually look in the data in ever-increasing detail and uncover more and more interesting relationships. So you can go into quite some detail with this. Now the variance components themselves are really, really useful. They become a really sensitive indicator of the consistency and the quality of your production. And essentially what you're able to do is you're able to summarize your production as basically a sum of the variances from the different sorts of process inputs. Which is really, really useful because you can see how that changes across time and across shifts and across lines, and you can and you've actually got something which might be the start then of a quality function. Something which actually looks at how consistent your quality is over time rather than just looking at the variance. Now, there's all sorts of other stuff as well. That thing about ad hoc variance targets, anyone who's worked in production will often know that if you're responsible for a process, you need to run it within a particular capability. But often your spec limits on that process are often set like by some, plus or minus 1% sounds good. But we start to have these full variance models, and we can do things like we can partition variance across the production. We can have realistic variance targets. We know what the genuine capability actually is of all of our processes. We can target how to improve them. There's lots of things we can actually do. Okay, now there's so much information in this other vectorial data set about underlying noise, which is really, really important too. Particularly because in some of this data, there's some particular measured aspects of this data which are highly noisy, okay, and you can actually start to see that. Often they're things that you take as accurate, but you can see in the way the data behaves that it's very noisy. Now in the case of this data set, we can check some of the results that we get where we can solve all of these models. We can look for these relationships and start to solve these models for proportions of variance that we get in this data. Now, the other interesting thing that we can do with this data set is some of this data have sort of measured analogues, if you like, in the data set. So there's some measured analogue for lifetime. There's some measured analogue for the emitter resistivity, the wafer resistivity, because this data set is all joined, and you can start to therefore have a comparison with what the latent variable model did and what the measured data did. Now, it's not very good, is it? Like, I should have just left this slide out and then you would have been much more convinced. But what's interesting, this in itself is a really interesting result, the difference between all of these things. The broad trends in contribution are fairly similar, okay, but there's some really interesting differences between what you get out of a latent variable model and a measured variable model, okay. One of the things is the latent variable model is only as good as the sum total of our knowledge about all of these interactions, okay. The other thing is that you can use the measured data in another way, which I haven't sort of gone into here, which is you can use it to test all of those underlying relationships that we were identifying in that data mining exercise. And largely, those relationships are pretty good, okay? So where these variance components fall apart is largely related to the underlying noise in the measured quantities, okay? So there's lots of ways that we can use measured data, latent variables together to make these models more and more accurate, depending on what data we have at our disposal. As I said, both of these have advantages and disadvantages. You know, a lot of these measured data models rely upon having joined data sets, which are not common everywhere. Okay. The most important thing is, well, as I talk, sorry, the most important thing is the next point, which is that you know, this whole thing about the measured data confirms the relationships. I mentioned that before. This point that the latent variable approach allows us to actually look at these underlying relationships and to track them, even if we have some doubts about their root cause. Okay, we can at least track them and identify them. And as I said, doing this over time is a good thing about quality. Is a good indicator of quality. Now, I'm probably out of time, aren't I? I am. Sorry. Okay. This second last slide. So it's really important that these sort of using these latent variable approaches and this sort of interrogation of the data doesn't invalidate the need for inline metrology. Okay. It can help you choose what you're best off using. Okay. And it can help you check out how accurate and valuable your inline metrology is. Okay. Now, the variance analysis is a very sensitive indicator of the quality, and obviously this data can be used to optimize the quality in the manufacturing. I'm really interested in this idea of what is a minimum, what's our best minimum data set, you know, because there's an answer for this when you're trying to improve the cell efficiency, and there's another answer when you're trying to keep the variance under control. They're actually two different answers, you know. And coming back to this idea of what's our best quality function. Now, I'll skip that one. Now, the final steps that I need to do in all of this sort of stuff is, you know, this needs to, you know, I've talked a lot about this in the two-dimensional sense, but there needs a more coherent, multi-dimensional treatment of this, which I've only just started with, because it relies upon on a bunch of statistical theory, which is called directional statistics, which has a whole bunch of analogues to normal statistics, but it's a good way to transform the data and rotate the data but we need a good, coherent, multivariate approach rather than this pairwise approach. And obviously extracting the noise is really, really important as well, because that's a really important outcome. Now, the best way to test these algorithms is to just keep using them, you know, get massive sets of manufacturing data, break it up, test it in different contexts, and look for how the models perform. You basically will find errors with the models pretty quickly by doing that. And then we try to, you know, obviously we want to code them in the front end and get people interested in using them once there's that statistical rigor behind them. Okay, and also the other steps, and I don't know how much of this I'll get to in my thesis, but a lot more work needs to be done about joining these data sets in the field performance and how this relates to manufacturing decision making, because there's some big disconnects here. So I've sort of talked about that a little bit in this. There's a couple of ideas there, but I think that's all I've got. Thanks. Sorry, I've run late.
I'm not sure if we have class after us, so maybe one question and the rest you can just get right after.
Just have to come and get me afterwards.
Someone?
Yeah.
Thanks, Rhett. That was very interesting to see what happens in real life.
Yeah.
Millions of points. One of the things that I don't quite get is if you can start with an analytical model, because we can model all the things that you put there as possible variables, right?
Yeah.
And then you put this through a random generator in variance, and then you check your models first on clean data.
Yeah.
And then try to apply it. Why not go that way instead? It looks like here you're being limited by the noise.
Yeah.
And so then you cannot tell whether the model is good or not because of the noise or because your model is not good, right?
Yeah, no, it's an excellent question, and like it's where I started. You know, when I first started looking at these sort of manufacturing data sets back in sort of when we first started doing work for Suntech back in 2010, started with exactly that approach. You know, building an analytical model, feeding, you know, some characteristic variance into it, and looking at how the thing spread. Okay, and it works really, really well. Okay, so largely you can use something like that as a starting point, but you also want to allow that to drift too from its starting point, because that's where you'll often find the interesting information. So, so for instance, you can use something like the relationship in the current and the voltage to actually refine your model in the first place, much the same way as, say, normally we would use, say, an EQE curve or an IQE. We would use some other more detailed piece of characterization to refine our cell model. We can use some of these relationships to refine our cell model as well. So, like, you're absolutely right. It works really well as a good first step and a good way to start the process. And you just need to find ways to allow them to interact. Okay, but it's a great advantage that we have. It's why, like, I would always really eschew any use of things like machine learning and stuff, because as soon as you start to go down just the statistical number crunch, then you give up on the physical models that we know about, and there's so much valuable information there. Like, it's you're exactly right. Yeah.
So let's thank Rhett again, and we will bring him in the end of the year to get.
Really, you want to sit through that again?